Okay, let's see. This is lab 5 on Newton's, I guess we can say Newton's second law. Okay, so let's first state what Newton's second law is. The statement is the following. The acceleration of an object, is directly proportional to the net force I'll put down here what I mean by net force. F net is the sum of all the forces acting on the object acting on it and inversely proportional to its mass. So that's the statement of the second law, and to put it mathematically, the acceleration is proportional to the sum of the forces divided by the mass, or equivalently the sum of the forces equals mass times, or rather, let's be, is proportional to the mass times acceleration, or the sum of the forces, and here's the equality statement, is some proportionality constant K times MA. And now the choice of the proportionality constant is entirely arbitrary, and for the units that we wish to use, we are going to say let K equals 1, and therefore Newton's second law, the statement of it is that the summation of all the forces acting on an object equals MA. All right, so that's the statement of the law. An important point here is that the second law holds independently for each coordinate direction. And therefore, I can say the following, that the sum of the forces in the x direction is equal to the mass times the component of the acceleration in the x direction. The sum of the forces in the y direction is equal to mass times the acceleration in the y direction, and similarly in the z direction, f sub z, the sum over f sub z is ma sub z. Okay? Now, one further point, and that's the following, and that is that suppose the summation of the forces equals 0. Okay. Then what happens is that the acceleration, which is the sum of the forces over m, is equal to 0. And what does a equals 0 mean? A equals 0 means that the velocity is constant. Okay? And of course, that constant could be 0. So this then is the statement of Newton's first law. Okay, so let's put down here, this is NFL, nothing to do with the football league. Okay, so now there are 3 parts to this experiment, and let me first talk about part 1 of the experiment. I'm going to assume you know Newton's third law. So let's talk about part 1. I'll start here. I think I have enough space to make some points here. Let's talk about part 1. What part 1 does is that it's about an object of mass m on an inclined plane. And so let me draw an inclined plane. This is the plane which is at an angle theta, and now I have an object here of mass m. Let me put that over here. All right, and I'm going to assume that this plane, there's friction between this plane and this mass m. Right, and so the first thing I want to do is I want to draw all the forces that are acting on this object of mass m, and the first force, of course, is its weight, which is mg. There is another force, which is the force of the surface on the object, the normal force. Okay, you've studied that in your lectures. So that's the force which is normal to the plane, and I'll call that N. And because I said there is friction between the two surfaces, if there was no friction, then this object would simply slide down. But because there's friction, it remains stationary on the plane, and I'll call this force F. So there are 3 forces on this object: its weight, the normal force on it due to the surface, and the frictional force. Okay, and as you all know, one defines the frictional force as some frictional coefficient times the normal force. Okay, and all right. Now, what I want to do next is that I want to break up these forces because they're all at different angles and what have you. So let's choose a system of axes and decompose these forces into components parallel and perpendicular, and then I can go back and use this expression above, which says that the law is holds independently for each coordinate direction. Okay, so let me where should I do this? Let me do it over here. Let me do it over here. Okay, so this is my angle theta. This is m. This is the object of mass m. And now what I want to do is I want to choose an appropriate direction for the axes. And let me choose the axes to be the following. Let me choose this to be the y direction, and let me choose this to be the x direction. Okay? This is entirely arbitrary. No one says that the x direction must be in the positive direction. I consider this now to be the positive direction. Okay? And so I see that the force, this is my force mg. This is the weight, right? This is the weight. This is the normal force. So the normal force is in the y direction. The frictional force, because it's not sliding down, is in the negative x direction. And now what I want to do is I want to break up this vector into its y component, okay, and its x component. And if I knew what this angle was, okay, if I knew what this angle was, then I could do it. Let me. So let's say this angle, okay? So I want to know what this angle is. If I knew that angle, then I could write down what the components are. Now that angle turns out to be equal to theta, all right? This angle turns out to be theta. And if you're wondering how that's possible, let me show you why that angle is theta. So let's draw a right triangle first, and you will see that the picture looks very much like the one above. So I'm going to draw a right triangle. Okay, let's call this A, let's call this B, and let's call this C, and let's call this angle theta, so it looks exactly above. And I said this is a, oops, why is that happening? All right, sorry, this is, and this is a right triangle. All right, and so let me call this angle phi. So I can say the following, that in triangle ABC, because this is a right triangle, theta plus phi equals 90 degrees. Now let me drop a perpendicular onto the side AC so that this angle is 90 degrees, and let me call this D. And so I look at the triangle, I say in triangle BDC, and I want to determine this angle, and let's call it alpha. I know from this right triangle that alpha plus phi equals 90 degrees. And therefore, alpha equals theta. And so that's why I can say that this angle up here, this angle up here, this angle is the angle theta. Once I know that, then I know immediately that this component is mg cosine theta, and this component here, the x component, is mg sine theta. Okay? And so now, as in all the problems that you're going to be doing, you have to draw what is called the free body diagrams. Okay? So let me draw the free body diagrams, or free body diagram in this case, since there's only one body. Let me draw the free body diagram, and I'm going to do it, I'm going to just make it horizontal. That is, here's my object, here's my object of mass m, and I now want to write down all the forces acting on this object. Well, I have this force here, which is mg cosine theta. I have this force over here, which is the normal force. Let's be absolutely clear. We had defined this as the y-axis and this as the x-axis. Then there's this force here, which is mg sine theta, and then of course there's that frictional force Ff. Okay? Now, let's consider the case when there's no motion. Okay, so let's write that down. Let's consider the case of no motion. No motion on the inclined plane. That the object, the frictional forces are equivalent to the downward forces, and consequently there's no motion. So let's consider that case first. And so let's write down the equations in the x direction. The equations in the x direction are the following. It's mg sine theta equals the frictional force, and I'll call this equation 1. In the y direction, the normal force N is upwards, mg cosine theta is downwards, so you have mg cosine theta, and I'll call this equation 2. All right? Now, since there is no motion, so let's write that down. Since there is no motion, one can define the frictional force as equal to the coefficient of static friction times n. All right? And from equation 2, I can put the value of n as equal to mg cosine theta. So this then becomes mu s mg cosine theta. All right. So therefore, 1 becomes the following. It's mg sine theta, which is equal to ff, but f friction is mu s mg cosine theta. All right. And what you notice is that there's an mg, there is an mg on the left side, there's an mg on the right side, they disappear. So then I have from this, what's remaining is that mu s is equal to sine theta over cosine theta, and sine theta over cosine theta is tan theta. I wanted to call this equation 3. Let me call this equation 4. And therefore, I can say that theta is arctan mu s. I'm going to put this in the box. So what's happening here is the following. I start increasing the angle theta of the inclined plane, and as I continue to increase it, it still doesn't move. The object still doesn't move. Then what happens is that the coefficient of static friction increases, all right, so as to satisfy equation 1, all right? That's the equilibrium condition, right? At some critical angle theta minimum, sliding will begin, okay? So at let's write down at theta minimum, sliding begins. So let's put down here, increase theta at some theta minimum, sliding begins. Okay, and so there's a maximum value for the coefficient of static friction. All right, so let's write that down. So because it increases with increasing theta, and at a certain critical theta, the sliding begins. So there is a maximum value of mu s. Now, once the sliding begins, the friction becomes kinetic. So let's write that down. Once the sliding begins, the friction is kinetic. Okay? And the coefficient of kinetic friction, mu sub k, is less than mu sub s. So part 1 of your experiment is to determine on an inclined plane the value of theta minimum, as they refer to it in the manual. Okay? All right. That is, they'll give you a value for the coefficient of static friction, and you are asked to determine theta critical, theta minimum. Okay. Now let's go on to part 2. Part 2 is also an experiment on an inclined plane, but in this case, let me draw it for you over here. In this case, here's our object of mass m, and this is my angle theta. But in this case, this object of mass m is attached through a pulley to another mass over here, small m. Okay? And let's now consider the case of, say, motion downwards. All right? So first let's do motion downwards. And since I've chosen motion to be downwards over here, let me then consider again my axes to be the following. My axes to be y going up perpendicular to the plane, and the positive x direction in this direction, just as I did in the previous case. Okay, so now let's write down what are all the forces acting on the two bodies. Well, we know this. We know that there's this downward force, which is the weight, which is mg. There's this normal force, which is n. The object is going downwards, and friction always is in the opposite direction. So here's my FF, my frictional force. And then, of course, it's also attached by a string to the other mass. And so there's a tension force in this problem, which I will call T. All right. And what about the second force? Well, the second force, there's a downward force of its weight, which is mg. And there's the upward force due to the tension in the string. The string is pulling it up. All right? And so once I've chosen my axes, I want to get rid of this. And I want to break it up into its y component, which is mg cosine theta, because I know that this angle is theta, and its x component, which is mg sine theta. Okay? And so let's draw the free body diagrams. I'll draw them over here. Free body diagrams. This is the critical part of any analysis. If you get the free body diagram correctly, you're in business. So here we go. Let's do the first one first, capital M. So this is capital M. This force down here. Remember, In this case, what we are doing, our coordinate system is y is up and x is this way. Okay. There's my, oh, I'm sorry, I didn't finish this. This is mg cosine theta. This is n. This is mg sine theta. And then I have my ff, and there's the tension T. Okay, that's for this body. And for the other body, the body of mass small m, you have mg and T, and I can just assume upwards in this case is positive y. Okay, that's positive y because the object is moving downwards, and so the small mass is moving upwards. Okay, so I assume the direction of motion to be the same as y positive. Okay, and so now let's sit down and let's write down Newton's second law for the object of capital mass m. So I'll put that down here, m, and we'll say let's write down the equation for the x direction. And the equation for the x direction is the following. Remember, the object is moving down the plane or to the left in the second figure. So you have the equation becomes mg sine theta. Now I'm summing all the forces in the x direction for the object m. Then there's minus t in the negative x direction, minus ff in the negative x direction, and this is equal to the mass of the object times the acceleration of the object. Okay, now the acceleration of both objects is the same because they're tied by this string. All right, so I'm not going to say a sub x, I'm just going to call it a. Okay, and in the y direction, the equation is n, which is upwards, downward force is mg cosine theta. Okay, so n equals mg cosine theta. And so let me call this equation 6, and I'll call this equation 7. Now let's talk about the equations for the small mass m. The small mass in the y direction in the y direction you have t going up minus mg going down equals ma. That's the net force on the left side, and ma on the right hand side. And so I'll call this equation 8. And now what I'm going to do is I'm going to add equations 6 and 8. So if I add 6 and 8, what I notice is the following. There's a minus t here and there's a plus t here, so that cancels out. So then I have mg sine theta minus ff from 6, and there's a minus mg from 8, and on the right hand side, when I add the two quantities on the right hand side of the 2 equals 2 signs, I get m plus small m times a. And therefore, I can write a as equal to as follows. I can write it as mg sine theta minus ff minus mg all divided by m plus m. Okay? And let me call this equation 9. Okay. Now we know the following. We now know FF, the frictional force, is now the kinetic coefficient of friction because it's moving times n. Okay. And this is equal to mu k. Now, what is n? Well, n is given to you in equation 7. N is simply mg cosine theta. Let's call this equation 10. And now if I substitute this fk into 9, I get, so I'll say therefore A equals let's see, mg sine theta minus ff. Ff is mu k mg cosine theta minus small mg all divided by m plus m. All right, and let's see if I can simplify this equation, and I believe I can. You notice that the first two terms in the numerator on the right hand side have an mg in it. Okay, so let's pull it out. Let's pull out the mg. Okay, and so what's left inside here in the parens is sine theta minus mu k cosine theta. Okay, I've pulled out the mg since it's common. Minus mg divided by m plus m. Okay, and this I will call equation 11. And this is one of the equations that you are asked to play around with. Okay, one can determine t. So let me just write down here that t may be determined once you know A. T can be determined, so I'll say T may be determined from equation 8. All right, so you know A, you know small m, you know G, you can determine T. All right, okay, let's now go on, and let's now do the same problem with the exception of the fact that the motion is now upwards. Okay, so let's do the case for the motion upwards, and I'll write down here motion upwards. So let's now draw the free body diagram. So I won't go over the whole process again. I'll just draw the free body diagrams. Okay. Now everything is the same as before, except the following. Well, let's do it. here's mg, here's m. So this was mg cosine theta. All right. This was n. Now, well, let's put this one down first. This is mg sine theta, but now the object is moving upwards or to the right, and so we have here the tension T to the right, but now the friction must be to the left because the object is moving up, or in this case to the right. So since the object is moving to the right, let me then define my axes as this, because it's moving to the right. So the equation writing becomes trivial. And the free body diagram for the second equation, second body, this is mg downwards, this is m, and this is t upwards. And if you like, I can now say, since this object is going down, I can say this is my positive y direction. Okay. All right. So now let's write down the equations. The equations are quite straightforward. Let's write down for n. You will notice a very nice, I guess, symmetry. Okay, so let's write down the equation in the x direction. In the positive x direction, right, because it's going to the right, so you have t to the right minus mg sine theta to the left minus ff to the left equals ma. And we'll call this equation 12. Now in the y direction for this object, y direction for this object, n equals mg cosine theta. For the object of small mass m, we're just talking about y direction. Okay. Remember, the object is going down, so my equation becomes mg minus t, right, equals small m times a. So if this equation was 13, then this equation should be 14. And now I do the same old trick as before. I said, let's add 12 and 14. All right. And if I want to add them, I notice that there's a plus t over here, there's a minus t over here, so those two cancel out. Oops. Sorry. Okay, and so if I add them up, I get there's an mg in the second equation, which is positive, then there's a minus mg sine theta minus an ff, and on the right hand side once again I get m plus small m times a, and therefore a equals mg minus mg sine theta minus ff divided by m plus m. Now once again we know now ff is mu k n, just like before, and n of course is mg cosine theta from 13, so this becomes a mu k mg cosine theta. And so let me now substitute ff so I want to call something 15. Let me call this 15. So I want to substitute 15 into the previous equation, and therefore I get A equals mg minus mg sine theta minus mu k mg cosine theta divided by m plus m. Okay, and again I can simplify this equation, or simplify how it looks. I can write it as mg minus, now look at what happens on the second two terms on the right hand side of the numerator. There's an mg there, there's an mg there, the sine theta and the cosine theta terms. So let me pull out the mg. So pull it out, and what do you get? You get sine theta minus mu k cosine theta. Haha, same thing as we got last time. And so divided by m plus m. Okay, and I'll call this equation 16. So now what I want you to do is I want you to compare 16 to 11 on the previous page. Okay, all right, and I can say one more thing. You'll see exactly what the symmetry is. All right, the two terms in the numerator are switched essentially. Okay, because in one case it's going down, in the other case it's going up. So you see how nicely everything fits in. Okay, okay. Now part 3. Let's see, part 3. No. Let me just make one more point. Of course, t can be determined from equation 14. Okay, let me just put that down. T may be determined from 14. Okay, and finally let's talk about the following. If there is no friction, okay, in all the stuff that we've done so far, if there is no friction, the term involving, let me just put it over here. If there is no friction, the term involving mu k vanishes, right? Because there's no coefficient of friction. So if I want to consider the special case where there's no friction, I take all these expressions that I've derived for, say, the acceleration, and put mu k equals 0, and voila, I've got it. I've got all the equations for that case. And finally, there is part 3, and I believe I should be able to squeeze it in here. Okay. This is a special case of motion upwards. All the stuff that I just described to you above. Okay? And I want to talk about the special case in which there's no incline. That is, theta equal 0. And let me just remind you that sine 0 degrees is equal to 0, right? And cosine 0 degrees equals 1. Okay, so this is a special case of motion upwards. All right, for theta equals 0. So then from 16, comma, a then equals, well, now I'm going to put theta equals 0 in the expression in 16. It becomes mg minus mg times sine theta, well, that's 0, minus mu k cosine theta. Cosine theta is 1, so this simply becomes minus mu k divided by m plus m. And this is equal to mg, the minus and the minus is a plus mu k mg over m plus m. Okay, and this I can write as follows. Let me pull out the g in the numerator. If I pull out the g, what you notice is that I can rewrite the numerator as m plus mu k m. The denominator is still m plus m. And notice that there's a g which is common, so I'll pull it out. Okay. And if you look at this expression, the numerator in the parens is smaller than the denominator because there's that mu k. Mu k is a coefficient, right? It's less than 1. So the quantity in parens is less than 1. And therefore, the acceleration in this case is less than g. Okay? And so part 3 of the experiment is you're going to do this special case. But you don't have to struggle with the equations because you've already done them. All you have to do is put theta equal to 0 in the above equations and you're done. Okay, so those are the 3 components of the experiment that you're going to be playing around with this week. Okay, take care. Bye-bye.